Sure.
All right. So I wanted to say a few things before we start. First of all, your homework, I believe, is due tomorrow. Don't forget that. And then you're mostly home free. You still have your little test coming up. It's a week from today. And then your project skills where you are enrolled in the 12-year option. Any questions? Yeah.
Are you a TA? Sorry.
I haven't decided. I'll let you know by what. The little test is going to be very different from the midterm. The little test is going to be all multiple choice or true false. So I'm not sure whether a cheat sheet would completely give away the answers to a lot of them. So I'll let you know on Wednesday. On Wednesday we can talk more about the little test. Other questions? All right. So I'd like to introduce Aditya. Aditya was the TA for this course for the 2 years previous to this one. He's an expert on convex optimization. Today he's going to be doing us the favor of teaching us about fast stochastic methods as requested as we voted on last time.
Cool. Hi, thanks. Thank you, everyone. So I'm going to go a little slowly in this lecture. The idea will be to at least give you some intuition about a recent line of work over the last, maybe 3 or 4 years, mostly actually in the last couple of years, and its importance for machine learning, as well as convex optimization, but maybe more specifically for machine learning. Okay. So if you have any questions at any point of time, feel free to stop me. The notes are online, so you can follow the notes. I'll just be kind of following the same outline as the notes. So you can look at the printouts while I'm using the whiteboard, but feel free to stop and ask questions at any point. I'm not planning to go very fast. Okay. So this lecture is going to be about minimizing finite sums. Okay. So it's about minimizing finite sums. Yeah, and also if you can't see this, then any part of this, just let me know. I'll try to write it bigger or something like that. So a finite sum is something like this. Okay, so this is the function that maybe I should write of w. Okay, so f of w. And so we're trying to minimize minimize f of w, and w is in a d-dimensional space. And this kind of problem arises in a lot of places in machine learning. Can people give me examples of different kinds of FIs that we might encounter? Anyone? Empirical loss. Can you give an explicit example of such an FI? The negative log likelihood. Cool. All right. So it can be the negative log likelihood. But what is the Fi? Why is there an Fi over there? Like, what would Fi of W stand for? Like, what would that mean? Anyone? IID samples, sure. So can you give me an explicit example of this? Say, if I was using the squared loss or something like that, what Fi of W would mean? Sure. Okay. So here's an example of this term. It would be yi minus xi transpose w squared. So I have n data points, xi which is d-dimensional, yi which is real valued, say, and w is my linear predictor. I'm trying to find the best linear predictor. So I use the squared loss, and that's an example of this. Can anyone else think of some? So this is what people call regression. Can anyone think of a different setting where you have Fi of W? Even if it's obvious, this should be obvious. If it's obvious, please go ahead and speak out. I'm not saying anything very deep here, but I want to see how many people are familiar with the machine learning setup. Anyone? No? Okay, classification. Does anyone know classification? Do people here know classification? Raise your hands if you do. Okay, so can anyone give me an example of a classification problem that can be posed like this? Sure, logistic loss. Can you spell that out? Okay. So I mean, I'm assuming people have seen things like this in the lecture, in the course before. Okay. Okay. All right. So this is say logistic regression. This is just least squares regression. SVMs, if you have heard of that, fits into this also. This is what's called the hinge loss on the data points xi, yi. And again, you're trying to learn a linear classifier W that separates your points in an SVM. Right. So there are many examples in classification and regression which can be posed in this fashion, right? So that arise naturally in machine learning. Now it's very important to remember that this lecture is about minimizing this particular quantity f of w, which is also called the training error. In machine learning, we are more interested typically in minimizing the test error. Okay, and the test error is usually given by an expectation of a loss function where you have, say, x and y drawn from a joint distribution P, and the loss of your predictor W on the new points x and y, and you want to minimize this overall W. So this is the typical framework of machine learning. You have a loss of your predictor over some set of points. So set of points are chosen randomly from a distribution, and you want to minimize this expected loss or risk, and you want to find the best such predictor. Both classification and regression kind of fall in this framework. And since we can't minimize the test error, sometimes we try to minimize the training error. Okay. Another common trick that people, not trick, or a technique that's used is regularization, where instead of minimizing the training error just as it is, people will often add a regularization term of this kind. So this is called like a ridge penalty. And so we'd be interested in minimizing things like this also with a ridge penalty, which is usually there to prevent overfitting. But of course, this talk, I'm not going to talk about how to choose lambda. Okay, that's a very important problem. How do you pick lambda to minimize overfitting in some sense? But we're going to assume in this talk that we are given xi, yi and data points, and we are given lambda, and all we want to do is actually just solve this optimization problem. It's like regularized empirical risk minimization. Okay, so is everyone kind of on board with that framework? If you have any questions, this would be a good time to ask, because the entire talk is going to be based on things of this form. Okay, I shall assume that means everyone's okay with that. Okay, so there are a ton of algorithms to actually solve this. Okay, so let me just specify a few things that I'll use in this lecture. Is that I'm going to take Fi as differentiable. Okay, so at least for this talk, I'm not going to be referring to the hinge loss at any point. So you should think of this as a differentiable loss. Could be the logistic loss, could be the squared loss, things like that. And I'm always going to assume that there's this regularizer of lambda by 2w squared. So this particular thing you might have seen earlier in the course. This makes it strongly convex. So this makes the problem, this just addition of this ridge penalty makes it strongly convex, which means there's a unique minimizer, and a lot of nice properties also arise that you can minimize these things quite fast. And so I'm going to assume a common form that all of them have this ridge regularizer, and they're all differentiable. And further that the gradient is L Lipschitz, right? So I'm assuming that you guys are familiar with Lipschitz conditions, but it basically means that each of these Fi's satisfies something like this minus of W prime is less than equal to L times W minus W prime. Okay, so I hope you guys have seen these kind of conditions before, or you recall them at least. So this is just saying that the gradient of each of these Fi's is L Lipschitz. Okay, so this is like a smoothness condition. This can of course only hold if it's differentiable in the first place. So I'm going to assume that they're all differentiable, and L smooth is the term that's used in the literature. Okay. Any questions about the setup? Okay, so now that you're at the lag end of the course, a lot of you will already have ideas on how to solve such problems. So can you suggest some simple algorithms to solve this problem? Okay, so you're actually faced with this problem in real life. You have a data set and you want to solve one of these problems. What is one of the algorithms you could apply? And no answers from the TAs. Okay, somebody else. No, TAs and instructors get second choice. By any students? Gradient descent. Thanks, Jersey. Okay, great. So our first default option is gradient descent. Okay, great. So gradient descent will work as follows. We're going to calculate the gradient of f at our point w and take a step in the direction of the negative gradient, right? Now note that taking a gradient step involves calculating the gradient at each of the data points. Okay, so you have a predictor w and you have to calculate the gradient of each of those fi's. So there are n of these fi's and you have to calculate the gradient of each one of them and sum them all up and then take a step. Okay, so what's the problem with that? Can anyone think of any issues that gradient descent will have if you just applied vanilla gradient descent on this problem? What are the problems? What are the issues? Any concerns you might have? Absolutely, yeah. So what you should really think about is where you're like Google or something like that, and n is in the billions or more or something like that. N is just some massively huge number, and going through all your data points once to take one gradient step is extremely expensive. Like you'll probably spend hours just going through your data set to calculate one gradient. And then you have to calculate a gradient again to take the next step of gradient descent, and then you'll go through all those billions of data points, calculate one gradient again and take your next step. Okay, so this is for Google or Facebook or in a lot of machine learning applications. Even it doesn't even need to be that scale. It could just be you're dealing with neuroscience data, which is a few gigabytes large. Going through gigabytes of data that's stored on your hard drive just to calculate a gradient is a bad idea. Okay, so that's basically the motivation behind alternate methods to solve this problem. Okay, it's just that the trivial thing that you would do, which is just calculate the gradient, take a negative gradient step, it's a bad idea because it will just take forever to calculate those gradients. Okay, so what we're going to try to do is develop algorithms that don't look at the whole data set at every iteration. Okay, because it's just extremely expensive. So that kind of gives rise to what's called stochastic gradient descent. Okay, so let me write that out here. So that's stochastic gradient descent. So I noticed that you guys did see this at some point earlier in the course. Does anyone want to volunteer what a definition of stochastic gradient descent is, or an example of it applied on this problem? It was in the subgradient chapter. Yep.
So each iteration, rather than evaluating all the contributing functions, just choose a single data point or a batch of data points and evaluate.
Right. Okay. So just to rephrase what Dallas said, at each iteration, instead of evaluating the whole gradient, I'll just pick, for example, a random one of those data points and just evaluate the gradient at that data point and take a step in that direction, right? So this is what it would look like. It would just be like Wt plus 1 is Wt minus some step size. Okay, we'll talk about how to set that step size later, and times the gradient of Fi at Wt. Okay, so instead of calculating the entire sum or the entire average, I just take one of them at random. So pick I uniformly at random from 1 to n and take a step like this. Okay, so clearly each iteration, instead of taking time n times d, okay, so remember over here you have n data points, each of them is d-dimensional. So you're literally taking n times d time to look through your whole data set. Here you're just taking time d to take one step, right? So you just order d. That's the cost of this iteration. Okay. Now, if any of you have seen the analyses of gradient descent and stochastic gradient descent, you'll know that gradient descent is fast. And what do I mean by fast? I mean that if it's smooth and strongly convex, like I just said that I'm going to assume that it's smooth and strongly convex, then gradient descent converges at a linear rate or an exponential rate, sometimes it's called. And that rate just looks something like L by mu, which is like the condition number of the problem, times log of 1 by epsilon. So that's the number of steps that gradient descent takes to reach an accuracy of epsilon. Okay, so maybe I should write that as lambda. So lambda is the strong convexity parameter. So even if this function is not strongly convex, the entire function f of w is strongly convex with parameter lambda. Okay, so if you don't remember this, then it's quite easy to prove that if you add a ridge penalty with a lambda there, the function just becomes strongly convex with parameter lambda, at least lambda. It could be larger, but at least lambda. And actually, it's quite easy to show that it's also probably L plus lambda Lipschitz, something like that. But basically, the number of steps that gradient descent takes to reach an accuracy of epsilon is log of 1 by epsilon times some kind of a condition number of the problem. Okay. Unfortunately, as we said, that this takes like n times d time to calculate, right? So like each of these, actually you should think of as each of these iterations takes n times d to calculate the gradient, and so that's like the real computation is this. However, on the other hand, this one is really cheap. Okay, so each iteration is not n times d, but just order d, right? But the number of iterations that this method takes, stochastic gradient descent takes, when the function is smooth and strongly convex, you can show as 1 by epsilon. Okay, so there are some other factors over here, like which involve the geometry of the set. If you have a set that you're projecting down onto, and like the Lipschitz constant also, I think that it should just be like something like L by epsilon and things like that. But broadly, 1 by epsilon is exponentially worse than log of 1 by epsilon. Okay, so if you think of epsilon as 10 to the minus 5, then this will take 10 to the 5 steps to converge, and this will take 5 steps to converge. So there's like no comparison between a 5-step thing and a 10,000 step thing. That's like even discounting the conditioning number part of it. But if you just compare log of 1 by epsilon and 1 by epsilon, like stochastic gradient descent is much, much worse, right? So you gained a lot by saying that each of these iterations is much cheaper, but you immediately lost a lot because stochastic gradient descent is just much slower than gradient descent. Okay, so a lot of people wondered if it was possible to get the best of both worlds. Okay, so is it possible to have an algorithm that looks at one data point at each step, that has order d computation time, and at the same time converges at a linear rate which has a log of 1 by epsilon over there? Okay. Now, clearly the reason I'm here is because the answer is yes, that there do exist such algorithms, and it's very exciting that people were able to develop such algorithms. But at first sight, it seems like there's a problem with stochastic gradient descent, and to correct that problem, it will be important to understand what the problem is. So what is wrong with stochastic gradient descent? Why does it suffer so much? Okay, so why does it hurt you so much? So anyone has any insights on that? Any thoughts on that? What's wrong with stochastic gradient descent? It's clearly taking an unbiased step, right? So at each step, it calculates a gradient gt, and gt is, I'm just calling this the gradient at time step t, and the expected value of gt is actually equal to the gradient of f at wt. Okay, so I'm taking a step in the direction gt, which is an unbiased step. I have an unbiased estimator of my gradient, which means that more or less on average I'm moving in the right direction. But why does it take so much longer to converge compared to gradient descent? Any thoughts on this?
Does it have anything to do with the fact that if the objective is strongly convex but the two individual ones are not?
That's a good point. Okay, I shall take back what stochastic gradient descent does. I forgot to add a strongly convex term over there. So it's this plus lambda times wt. Okay, so this is gt. So actually, thanks for pointing that out. I move in a direction where I differentiate, I take one of these at random, but I also add lambda times WT. So now the expected value of this guy is just the average of all of these, and it's, the average of lambda times WT is just lambda times WT itself. Right? So maybe let me write this down a little more explicitly. The expected value of GT, where this expectation is only over the randomness of choosing those, the ith point, is just the average of all of those gradients plus lambda times WT, and that's just equal to the gradient of F at WT. Okay, so it is an unbiased estimator, and it is working on a strongly convex function. Okay, so stochastic gradient descent is also using the strong convexity of the function. If you were not using the strong convexity of the function, suppose the function was not strongly convex, I had not added a ridge penalty, and it was not strongly convex, then the convergence rate of stochastic gradient descent is like L by root epsilon. So this factor of epsilon just becomes worse. So if you don't have strong convexity, it's square root of epsilon. But because there is strong convexity and it will exploit that strong convexity, it becomes L by epsilon. Okay, so yeah, that's not the exact reason. Both of them are working on strongly convex functions. Okay, so anybody else? That was a good try though. Anybody else? What's the problem with what stochastic gradient descent is doing? Why is it doing so much worse? Yep.
So you're computing the gradient only at one point. So even while in expectation it could be the same, but you could still be the direction of the gradient that you're taking would widely vary from what you should be taking. So you could, like in practice, you could go haywire while still in expectation you could get to the optimum that you were looking at.
Okay, so I just want to rephrase what he said in case everyone couldn't hear that. So what Mrinmay said was, this is an unbiased estimator of the gradient, but it has high variance. Okay, so I think you should think about that a little bit. I have an average of n quantities. Okay, so just imagine I have 10,000 different things that I'm averaging, and I ask you to estimate the average. And you just pick one of them and you say, okay, that's my estimate of the average. Okay, so just imagine I was averaging the numbers 3, 5, -1, 2, 100, and so on. So just imagine I was averaging all of these numbers, and I asked you to guess what the average was, and you picked a number uniformly at random, and you said, that's my guess for the average. You are unbiased, because in expectation you are correct, but you have extremely high variance depending on which of these numbers you actually picked. Right? So it's extremely high variance. So the reason that stochastic gradient descent does not converge well is, even though it's working with unbiased gradients, these gradients were evaluated on like one data point, and you have n data points, which is in the billions, for example. It's extremely high variance. You're like nowhere close to the right answer on, like, on average you are near the right answer, but any typical guess, as Mrinmay said, you'd be just shooting off in some weird direction. On average, you're going the right direction, but very high variance. And this variance is what really hurts you. Okay, so this variance is what hurts you. Any questions about that? I want people to, like, I don't know, imbibe that a little bit, that if you were taking an average of these numbers and you picked a random number, you're correct on average, but extremely, like, wrong in practice, I would say, like, just you're very high variance in practice. Any thoughts? So coming back to what Dallas earlier said, he said that instead of picking one data point and picking that, why don't you just pick some subset of the data points and work with that? So that's called mini batch stochastic gradient descent. So if you picked a batch size of B, instead of one data point to evaluate the gradient on, you pick B data points. Well, you reduce your variance by a factor of B, but it's nowhere close to, like, typically if n is in the billions, you're not going to choose your batch sizes in the order of even millions. It doesn't make sense. You'd probably choose small batch sizes. So you'll be killing your variance by a constant factor, but you're still nowhere close to a deterministic gradient calculation which has no variance in essence. Right? So like definitely mini batch stochastic gradient descent does work much better in practice than just plain old vanilla gradient descent. But yeah, it has its problems too, because the batch size has to be small enough for it to be efficient. And in that case, you're just cutting variance by a constant factor compared to gradient descent. Okay, so I'm now going to introduce some ideas that work, okay, some techniques that actually do work, and the reason that they work. So you're not going to remember the algorithm that I introduced to you. Like I'm going to spend like 15 minutes or 20 minutes talking about an algorithm. You're not going to remember it 2 weeks from now or a few months from now. What you should remember is the intuition. Why do those algorithms work? Okay, and the reason that those algorithms work is they're going to kill the variance. Okay, so they're going to still be unbiased estimators of the gradient, but we're going to construct those unbiased estimators in a way that as the algorithm converges to the optimum, the variance of the gradients goes to 0. Okay, so that's the reason that we are going to construct algorithms that work better than stochastic gradient descent. The reason is they're going to still be unbiased gradients, but as the algorithm converges to the optimum, the variance of those gradients is going to go to 0. Yep. Yeah, that's a good point. So if any of you are familiar with, say, Stein shrinkage or something like that, one of the common ideas in machine learning and I guess statistics is to add some bias to reduce the variance, right? So basically, we don't have to move in an unbiased gradient direction. We could move in a direction that's slightly biased as long as it has much lower variance. So that's also a good idea. And in fact, one of the algorithms will do that. So there's a particular algorithm which I'll introduce which does do that. The analysis is horrible. Like the analysis is like 15-20 pages long, and to verify one of their inequalities, they had to resort to a computer-generated algorithm to find constants that verified their inequalities. So the authors think that the reason that their algorithm was so hard to analyze was because they introduced this bias to decrease the variance. And there are these other algorithms, which I'll also talk about, whose analysis is much simpler, like 1.5, 2 pages long. I won't do the analysis here, but they're just very short. And they work with unbiased gradients and with low variance. So like, yes, you can definitely do what you said, which is increase the bias a little bit to decrease the variance. But it's all about, can you prove that they work well? Can you prove that your idea works? Yeah. So that algorithm works amazingly in practice, but the proof was mind-blowingly long. Yeah. Any thoughts? Okay, so that's gradient descent versus stochastic gradient descent. Maybe I'll just lift this up so that people can continue to look at it. Bring this down. Okay. So remember, that's our setup. L smooth Fs. Strongly convex because of the ridge penalty, finite sum, that's our setting. We want the best of both worlds of gradient descent and stochastic gradient descent. Cheap updates, linear convergence rates. That is the log 1 by epsilon kind of convergence rates. Okay. So there was a landmark paper, and it really is a landmark paper. It was by Schmidt, Leroux, and Bach in 2012. Okay, and this was called SAG. SAG stands for stochastic average gradient or something like that. So, but in the literature you'll just find people writing SAG. So might as well hear about it once. So it's the SAG algorithm, and the reason it's a landmark paper. I'll first tell you the reason it's a landmark paper. The reason it's a landmark paper is because there are lower bounds that exist for stochastic algorithms that say that you cannot, in general, beat the rates that stochastic gradient descent gets. Okay, so basically, why is it landmark, right? So there are lower bounds. Okay, so Nesterov, Nemirovsky, and Yudin in 1983. If you don't know Nemirovsky, you should. He's a giant in optimization. Nesterov, another giant in optimization. They've proved lower bounds for like stochastic algorithms, and these lower bounds have been improved over time to tighten the constants, the dimension dependence, things like that. But broadly, what these lower bounds say is that if you assume nothing but convexity, then a stochastic gradient algorithm A stochastic gradient algorithm is one in which you give a point W. Okay, so here's an oracle, and you input a point W to the oracle, and the oracle spits out a noisy gradient at the point W, such that the expected value of that noisy gradient is the true gradient of the function. Okay, so this is what's called a stochastic first order oracle. It's stochastic because it returns something noisy to you. It's first order because it returns a gradient information to you. And it's an oracle because it knows the function and you don't know the function. Okay, so it's a stochastic first order oracle. Stochastic first order oracle. And the way this works is that you ask for the gradient at a point W, and it gives you back an unbiased estimate of the gradient at W. And then you repeat. You ask for the gradient at a different point W, and it gives back a noisy gradient which is unbiased at that point W. And so this oracle is enough to do stochastic gradient descent, because you can ask for the gradient at W0, and then you get back a noisy gradient, you take a step. Then you ask for the gradient at W1, you get back a noisy gradient, you take a step. So this kind of oracle is enough to do stochastic gradient descent. It's also enough to do anything else that you can imagine, like collect all the gradients from the first 10 points and combine them in some intelligent way. So you can do like some fancy stuff. So you can do any algorithm that uses this information in pretty much any way you want. There's some limitation that has to be like linear span of those subgradients, but just let's forget about that for the moment. And there's a lower bound that says that there is no algorithm that exists, there is no possible algorithm that can beat a rate of 1 by epsilon squared for convex functions and 1 by epsilon for strongly convex functions. So this is just for convex, and this is for strongly convex. Okay, so the rate at which you get epsilon suboptimality, if you don't know anything about the function other than the fact that it's convex and you get unbiased gradients, then you can't beat 1 by epsilon squared. And if you know it's strongly convex and you get unbiased gradients, you can't beat 1 by epsilon by any algorithm. Like however intelligent you might be tomorrow, day after, you can never beat this. These are what are called information theoretic lower bounds. Okay, so that's what we have in stochastic gradient descent. We have a noisy gradient that is unbiased in expectation, and we get a rate of 1 by epsilon for strongly convex functions. So it seems like we have an upper bound, we have an algorithm that matches the lower bound. So it seems like we are done, like there's really nothing that we can do. Okay, but the real insight one of the insights rather that these guys had was this is what's called a worst case black box lower bound. Okay, so this is a worst case black box lower bound, and we know something more about the function than just getting unbiased gradients. We know that the function is of that form. We know that the function is a finite sum. So the function is an average of n data points. That's actually what helps us a lot. If that function was not a finite sum but an infinite sum, in some sense, if it was an integral, okay, so if you were somehow working with minimizing an integral, for example, you can't apply any of these methods. But because you're minimizing a finite sum, you know something about the structure of the problem. It is an average of some quantities, and you can use that insight to get past these worst case lower bounds. Okay, so for a long time, for a very, very long time, it seemed like what stochastic gradient descent was doing was not beatable, because there were lower bounds that said that when you get unbiased gradients, you can't beat it. And so people just did that and were happy with it. But then these guys came across a really simple algorithm, and they proved that you can beat the lower bounds. And that's because the lower bounds were worst case, while you know something about the structure of the problem that you can exploit. Okay, so what is their algorithm? Their algorithm was extremely simple. Okay, so at each step, you pick a random data point I and you evaluate gradient of fi. So you evaluate gradient of fi at your point w. Okay, so you evaluate just one gradient, but the step that you take, the wt plus 1, is going to be eta times, so some step, there's going to be a step size. I'm going to average from 1 to n of gi of w, where gi of w is gradient of fi of w if I picked I. Okay, so if I picked I at this step, so suppose I picked the 10th point at this step, then G10 will be actually the gradient, and it will be the old value of this gradient if I didn't pick I. Okay, so let's just see let's just try to understand what this is doing. This algorithm is maintaining n different gradients in memory. Okay, so it's going to keep n gradients in memory. But at each step, it's only going to update one of those gradients. Okay, n minus one of those gradients are going to be old. You updated them at some previous step. But the step that you take, instead of it being in the direction of just the point that you queried at, instead of taking, you queried at I, and you got a gradient. Instead of taking a step just in the direction of that gradient, you take a step in the average of the new gradient and some old gradients that you had kept around with you. Okay. Now, of course, the old gradients that you kept around with you, they're not super accurate, because maybe many of them were like from 10 times ago, 15 times ago, n minus 1 times ago, and so on. But a lot of them are going to be recent. Like you can think of maybe a large fraction of them are going to be from a recent point, and so they're pretty good estimates of the gradient at the current point, and many of them are really old. So this is in some sense what this was the first algorithm, like what Dallas was saying. It is not unbiased. Okay, so this is not taking a step in the unbiased direction of the gradient. Okay, so maybe I should have again added lambda times w. Okay, but basically it's not an unbiased gradient, because part of it is unbiased, but part of it is very biased. It's using some old information that is outdated. But somehow taking this average, even though it's biased, decreases the variance a lot. Okay, in general, averaging quantities really reduces the variance. Okay, so that's all the algorithm is. It's really just this. So at each step, you query it at one point, you update just that one point in your memory, and then you take a step in the average of all of them. Okay. Yep.
Are you summing over only the gradients you've seen so far?
Yeah, so maybe you should think about, you have one pass through the data in which you calculate everything, or you keep zeros. If you've never seen them, then you just think of them as zero.
Okay.
Yeah, so yeah, that's either you take one pass through the data once and then just evaluate all of them at W0 if you want. Just one time go through the data set to initialize the algorithm, and then after that you use the old values of the gradients. Or if you want, just treat them as zero or something like that. So yeah, I think you can look at the exact details in the paper of how they implemented in their experiments. Now, why does this not have memory issues? Fantastic. Okay, great. I was hoping someone would ask that question. Okay. So let's actually look at any one of those data points. Okay, so it turns out that suppose I have anything, least squares, logistic regression, any of these guys. Okay, almost any machine learning algorithm. I'm just going to represent it as some phi of xi transpose w. Okay, so all of these loss functions are somehow maybe yi times xi transpose w, something like that. All of them can be written as some function of xi transpose w. Okay, that's what the fi is. It's some function of xi transpose w. Now, if I take the gradient of this guy, okay, what is it going to be? It's going to be xi times, whatever, the gradient of this at a point w0 is going to be this times phi prime of xi transpose w0. Okay? And what does that mean? That means that I don't actually have to explicitly store this gradient. I already have all the data points. This is just actually, I can just store that quantity, which is just like a number. Okay? It's just a value. It's a scalar. Okay? So actually the way you implement it in practice is to just store these scalars, because you know that the gradient is just a scalar for each data point. And because you know that if you wanted to take a step in the direction of that particular gradient, you just already have all the data points. It's just a scalar times that data point. So implementing this in practice is very efficient because you don't actually have to store n different gradients in memory, which would cause n times d storage in memory. You can just store these n scalars, and then if you have to take a step in the direction of the gradient, you already have these data points. Also note that updating, if I've calculated this average at one step, then taking the next step, that update is really trivial because I'm only changing one of the guys in that average. So if I have this average from step t, when I go to step t plus 1, I'm only changing one of them. The rest of them are stale. So I only have, the way I update this is extremely trivial. I subtract the old gradient by removing some scalar times xi, and I add a new gradient by adding a different scalar times xi. So like it's just like the update is very quick. It's in order d time, and memory storage is not an issue. So it is true that in general, if I was not in the machine learning setting, and those were just different FIs, then it's true that I would have memory problems. But luckily for us, in a lot of practical scenarios, storage is not an issue. Okay, any questions? Okay, so I think this is a good time to pause. When I come back, I'll introduce a slightly better algorithm for this problem. So as I said, this was the algorithm that had an extremely long proof to it, like 15, 20 pages of proof, computer aided and so on. And they finally proved that you could get an exponential convergence rate very much similar to what gradient descent looked like, except that it was spending a single iteration at every, like a very cheap, looking at one data point at each step. But the number of iterations it needed for epsilon suboptimality looked like log of 1 by epsilon times some, condition number. So this got the best of both worlds, but there were still many improvements to be done after that, and I'll talk about those after we return. So maybe just take a couple of minutes break, go drink water, ask me questions, whatever, it's fine. Okay, so let's restart. I'm going to talk about a different algorithm. So after SAG was published, there was a huge sequence of works. So this was published in 2012. And if you look at the number of citations it has, it's like massive. It's like 50 plus citations. There was an algorithm published at NIPS in 2013, which is called SVRG. And that has like 60 publications in the last 1.25 years or something like that. So these things are like absurdly popular because they work really well and because the ideas are really awesome. So maybe following this up was something called SDCA, which is stochastic dual coordinate ascent, and I'll describe that algorithm right now briefly. And following that was SVRG, which is stochastic variance reduced gradient. And I would say that these are like the dominant algorithms right now. SAG was extended to what's called SAGA. So there's a paper from NIPS 2014 which is called SAGA. I think ICML at 2013 and ICML at 2014 both had SDCA. So if you just look at the recent ICML and NIPS papers, they've been pretty active with these three algorithms, I would say, which is SAG and its extension SAGA, and stochastic dual coordinate ascent, and stochastic variance reduced gradient. Okay, SVRG is kind of slightly more complicated to describe, so I'm not going to describe it because by the time I set up the notation, the class will be done. Instead, I'll describe SDCA, and it's an extremely simple algorithm. Like that's not the way it's presented in the literature, but there's a very simple way to think about it and look at it, which I'll describe now. Okay, so what SDCA, which is dual coordinate ascent, so what it's going to do is it's going to maintain dual vectors. So it's going to be a nice use of your duality. The proofs and stuff often use duality. And so they're going to maintain these set of dual vectors, and they will show primal convergence and dual convergence simultaneously. Okay, so I'll tell you what I mean by that. So our primal vector is what's W. That W that we're minimizing over there, that's our primal vector. And I'm going to introduce these dual vectors, one for each data point. Okay. But what is the motivation behind them? Okay. How did they come up with thinking about these dual vectors? Is just to look at that f of W and see what happens at optimality. Okay. So when we have reached W star, what actually happens? Okay. And that's given by just differentiating it and setting it equal to 0. So right, all I'm going to do up there is differentiate that and set it equal to 0. And you'll find that we get that lambda times W star is equal to minus 1 by n, sum from I is equal to 1 to n, times gradient of Fi at W star. Right? Does everyone agree that that's what's going to happen at optimality? Just differentiate, set it equal to 0. I'm just going to rewrite this by moving over lambda. Okay, so we just get that W star, the optimal primal variable, is an average of the gradient of Fi's at each of these W stars. Okay, at W star, sorry. So what stochastic dual coordinate ascent, very high level, this is again not the way it's introduced in the papers, but what it's going to do is it's going to maintain one variable for each of those. Okay, so what it's going to do is it's going to maintain the following equation. It's going to maintain sum of 1 by lambda n I is equal to 1 to n alpha I at time step t. Okay, so maybe I should write it that way. So at every time step t of the algorithm, it has a primal variable wt, and it's going to keep around these dual variables alpha it, such that there's one for each data point. Okay, there's one for each data point, such that the same thing, this average 1 by lambda n times the sum of alpha it is just equal to wt. Okay, and what they're going to show is that as the algorithm proceeds, wt converges to w star, and alpha it converges to minus gradient of fi at w star. Okay, so that's their aim of holding these dual variables, and they're going to use these dual variables in the updates. Okay, so why exactly they're dual variables and so on, I guess that'll come up in the proof and so on where it uses duality, but in some sense when W lives in one space, like the gradient of f at W is like lives in a dual space. I don't know, you can think about it in many ways, but these are what are called the dual variables. There's one for each data point. Okay, and so all the algorithm does, the algorithm is extremely simple to describe. Just like SAG, it's like a one-line update kind of thing. So what SDCA does is you initialize these alphas anyhow, right? So you have alpha I 0, so alpha 1 0 till alpha n 0. You just initialize them however you want, and you set W0 as this average. Okay, so the initialization for W0 is just an average of these guys divided by lambda. Okay, so it's a scaled average. And then you have to choose a step size eta. Okay, so this step size eta has to be chosen such that eta is less than 1 by n lambda. So this 1 by n lambda guy, so the step size has to be smaller than that. Maybe a different way of saying that is that beta, which is equal to eta n lambda, is less than 1. Okay, so if you just scale this, you get eta n lambda is less than 1, and sometimes the algorithm is described in terms of beta, which is just a scalar less than 1. So you know n and you know lambda, so you can choose this step size smaller than 1 by n lambda, right? So there's no magic going on over here. And sometimes they require this to be chosen as less than 1 by n lambda plus L, where L is the Lipschitz constant. But that's fine. Again, you know these quantities often, so they're easy to set up the problem, right? So you choose this step size, and then what you do is you choose random I from 1 to n, Okay, choose a random I, and then update alpha I. Okay, so update alpha I at t plus 1 as just alpha I at time step t, and then minus this eta n lambda times, what am I going to do? The gradient of fi at wt plus alpha I t. Okay, so let me see my notes to see if I got that right. You can just absorb it in the meanwhile, what the update is. Okay. That's it. That's the algorithm. That's all it does. I think, yeah, that's all it does. There we go. Genius. Right? So that's amazing. Of course, we have to update the W's to maintain this. Remember that we are maintaining this at every step. So I do have to update the W's accordingly. So Wt plus 1 is going to just be Wt minus, so there's a 1 by lambda n over there, so this will just be eta times probably just the gradient of fi at Wt plus alpha it, something like that. Any questions on what the algorithm is doing? Right, it's just updating alpha at each step and updating W just to maintain this relationship. Okay. Now, the algorithm is extremely simple. You can run it in practice and all of that. They prove a simple convergence rate. So they prove that it takes like maybe a couple of pages to prove, unlike SAG. And they prove that Wt minus W star squared. Okay, and there's some constant here. Somebody who has the notes can tell me what that constant is. And they'll add 1 to n. They'll take the average of all alpha it minus alpha I star squared. And there's some other constant here, which again, if you have the notes, you can tell me what that is. And they prove that this quantity, which is like the primal suboptimality at step t plus the dual suboptimality at step t, they show that this is e to the minus something times t, probably eta lambda t or something like that, times the same thing at step 0. So let's just call this pt and dt. So this is p0 plus d0. Okay. So the primal suboptimality at step t plus the dual suboptimality at step t is just an exponential factor times the primal suboptimality at step 0 and the dual suboptimality at step 0. Okay. So the good thing about this is it's an exponentially fast decay. Okay, it's an exponentially fast decay. And if you calculate how long this takes for Wt to approach W star and alpha to approach alpha and so on, then if you want the function to have a suboptimality of epsilon, then you just have to invert this. This is in terms of number of time steps, but if you write it in terms of epsilon, then you get a log of 1 by epsilon rate. And because it's an exponentially fast decrease, so you need only like log of 1 by epsilon steps to get there, and times something which I don't remember, but there'll be some condition number. There's some condition number here. So you can never escape this condition number. I mean, if the problem is badly conditioned, it is hard to optimize. So you will always, in any algorithm, pay for how bad the conditioning is. So there'll be a condition number dependence here times log of 1 by epsilon. Okay, so that's the number of steps that SDCA takes to approach an epsilon suboptimality. And maybe you're not, maybe you don't get the intuition right now of why this should work, but it's extremely easy to show, and I'll show you right now, that this is actually performing stochastic gradient descent. It is actually doing stochastic gradient descent where you have an unbiased gradient, but the variance is going to 0 as the problem approaches optimality. The variance of that gradient is actually going to 0. Okay, so let's try to see why that's true. So firstly, can anyone see from this primal step why this is stochastic gradient descent? In other words, I'm asking, why is this a stochastic gradient? Any thoughts? I claim that this is an unbiased estimator of the true gradient. Can anyone tell me why? If you can't see it, it's gradient of Fi at Wt plus alpha It. So I claim that that's an unbiased estimator of the true gradient. Any thoughts on why? People at the back? Last row? No? Okay, so I mean, let's just make a couple of simple observations. The true gradient is an average of all those gradient of Fi's. So when I take the expected value of this gradient, I get the average of all of these guys. So that's my first term of the gradient. And my second term of the gradient is an average of all the alpha i's. But I'm maintaining the fact that the average of all the alpha i's is in fact lambda times Wt. So I actually get back lambda times Wt, which is the second term, because I'm at every step I'm maintaining that lambda times Wt is the average of all the alpha i's. So the expected value of this, which is the average of all the alpha i's, is just lambda times Wt. So I get the first term of the gradient up there and the second term of the gradient up there. So it is an unbiased estimator of the gradient. Okay, so just like kind of pretty straightforward. If you don't follow this, you should ask me right now, because you should see that this is an instance of stochastic gradient descent. The authors themselves did not notice this for quite a while until SVRG came out and so on. And so this was all post SVRG that they realized, oh, what we're doing is actually an instance of stochastic gradient descent. That's because they didn't originally write the algorithm in this fashion. Okay, so that's cool. So it's stochastic gradient descent. The second thing I claimed was that the variance of this quantity goes to 0. Okay. So let's see why that's true. Okay, so why does the variance of this quantity go to 0? Okay, so let's have a simple calculation of that. So this is just the expected value of gradient of Fi at Wt plus alpha It square. I'm going to show that the expected value of x squared goes to 0. So if you remember your definition of variance and so on, like the variance has e of x square minus e of x the whole square in some sense, but that's upper bounded by e of x squared. And so if I can just show that e of x squared goes to 0, you'll be convinced that the variance goes to 0. Okay, so I'm just going to prove that e of x squared goes to 0. Like the corresponding version is just 2 norm squared of that quantity. This is a vector. Okay, so I'm just going to prove that that goes to 0. Now I'm going to do a simple trick, which is to add and subtract alpha star. Okay, so I'm going to let me just rewrite this. So I'm going to add alpha I star, and I'm going to subtract alpha I star, and keep that other term just there, alpha It 2 norm squared. Okay, so I didn't do anything great over here. I just added and subtracted the same term. So now I have 4 terms. And I'm going to use the fact that, I don't know, you should know this fact. It's just a plus b the whole squared is always less than 2a squared plus 2b squared. Okay, so this is just an inequality that you can verify for yourself by expanding it out, that this is true. So I'm just going to bound this by the expected value of the gradient of Fi at Wt plus alpha I star squared. Okay, so maybe twice this quantity plus twice of alpha It minus alpha I star squared. Okay, so an expected value here also. Okay, right, so all I did was I split up these terms into 2 parts. The first part has the first 2 terms and the second part has the second 2 terms. Now, at this point, it's actually, I can immediately conclude that this goes to 0. And there are two reasons why it goes to 0, for the first term and for the second term. For the first term, for the second term, it goes to 0 because of this convergence. So dual convergence shows that alpha it converges to alpha I star exponentially fast. So actually this term is going to 0 exponentially fast. So anyway, so we have this guy, which is just dual convergence of the ith coordinate. So that's going to 0 exponentially fast. Can anyone guess why the first term is going to 0? It's not obvious, but like maybe if you think about it, you might come up with some idea. So I have a gradient of fi at wt plus alpha I star. That's alpha I star. So why would this thing be going to 0? Okay? You should think about it for 5 seconds and I'll tell you the answer. Okay, so the answer is that at optimality, alpha I star, remember that I told you that the alpha it was going to converge to negative gradient of fi at w star. That's actually alpha star. Okay, so alpha I star is just the negative gradient of fi at w star. Okay, that's what alpha I star is. Now, can anyone guess why this is going to 0? So I have gradient of fi at wt minus gradient of fi at w star, 2 norm squared. Any thoughts on why this might go to 0? Because f is Lipschitz. No. Grad f is Lipschitz. Great. So we have one answer out there. The reason is that the gradient of f is Lipschitz. So that's what we assumed about the setup up there. That the gradient of fi at w minus the gradient of fi at w prime is just bounded by L times w minus w prime. So this quantity is just bounded by L times wt minus w star squared. Okay, so this first term is just twice L expected value of wt minus w star squared. And we know that this is just primal suboptimality. That's also going to 0 exponentially fast. Okay, so basically we have I just took the value of the gradient. I looked at the variance of that gradient. And I get that the variance the variance of the gradient is going to 0 exponentially fast because of primal convergence and because of dual convergence. So this is just intuition for why stochastic dual coordinate descent is working. It's just intuition. I've not proved this theorem to you. It takes 1.5 or 2 pages. But maybe the one takeaway, if you have to remember, like 2 months from now, why do these algorithms work? And the answer is because they're all calculating, they're all doing stochastic gradient descent. They're all taking steps in the direction, some unbiased estimate of the gradient, but the variance of those stochastic gradient steps goes to 0 as you get closer to the solution. So initially when you're very far away, it is noisy, but then as you approach the optimum, your variance goes to 0. Stochastic gradient descent does not have that property. At any time step of that algorithm, at any time, you're approximating an average by a single number. And at pretty much any time step of the algorithm, you have a large variance. Even if you're very close to the optimum, you still have a very large variance. But all of these algorithms, including SAG and SVRG and SDCA, they all work on the principle that you can still have unbiased gradients, but you can have variance going to 0 as you get closer to the optimum. That's the reason why they work. So that's what you should remember 2 months from now. The updates are, you can look them up. Yep.
So the fact that the variance of these estimates goes to 0 isn't really useful for the proof.
So actually for SVRG it is. So if you look at the proof of SVRG, the variance going to 0 explicitly turns up in the proof. If you look at the proof for SDCA, it's all muddled up. That's actually the reason why SDCA was first published in 2013 and about 2012, 2013, that range of time. And this was published at NIPS 2013. And then after that, the authors of SDCA realized that, I now realize that what we are doing is stochastic gradient descent. And I now realize that the variance of those gradients is going to 0. So they actually realized it in 2014 end or 2015. So this is a very recent realization that SDCA can be interpreted as a stochastic gradient descent algorithm where the variance of the stochastic gradients goes to 0. So it does come up implicitly in the proof. Definitely, it's absolutely important. The proof cannot hold without this observation. But it's not, let's just say it was not like the original proofs of SDCA don't have this outlined as a lemma and give this as intuition kind of thing. They have a proof that it works, but maybe now we understand better why it works. Sorry? I understand. Yeah, that's why I said this is just intuition. I have not proved this fact to you. This is just intuition for what's going on. They proved this fact kind of independently using a long and complex proof. But if you just go down into what's going on, this is the real crux of what's going on. You have an unbiased gradient whose variance is going to 0. That's intuitively why it works. This is not the proof, and like as I said, they don't use this as a lemma in the proof because it is circular, as I said. This is just intuition that you can take away for later. Yeah.
But if they use it implicitly in the proof, you can't prove
Yeah.
variance goes to 0.
That's right. So they don't prove that the variance goes to 0. They cycle around and show that the variance is just bounded by something in terms of the function value. So if you look at the SVRG proof, they don't have this explicitly. They don't hence say the last step is and hence going to 0. They don't say that. They don't do this. They instead bound this in terms of the function suboptimality. Because you have both strong convexity and Lipschitz-ness, you have upper and lower bounds. So you can replace any primal suboptimality by a function suboptimality. And so the proof is a little, like it doesn't use this, it doesn't say hence going to 0 at any point. It just uses this expression and substitutes that expression into the proof and does it. And then when you go back later after proving your proof and you look back at that expression, you're like, oh, I see that this variance is going to 0. So it's a post hoc understanding rather than a pre-understanding of what's going on. Okay. Any questions? Yep.
So this seems kind of weird because the alphas are the part that makes it different from regular
Right.
ND, right?
Absolutely, yeah.
Come through the regularity, right? The squared W term, right? They're sort of a running average of the gradient on that input, right? If you didn't have the alphas in there, this would just be cheated.
Yeah, so the alphas are like the gradients in some sense. Yeah, the alpha you should think of as the gradients, right?
It's like the gradient of the regularizer is W and the alphas add up to W, and so it's like having
That's right.
instead of W having P terms in it or D terms or whatever, you're giving its gradients N pieces instead.
Right.
But then instead of using all of W at each step as you would with regular SGD, you're using a different one each time based on which of the I's you chose. So it seems like this would add more variance because you're getting something different based on which I you chose each time rather than using all of W.
Yeah, so I would say rather that it is a coincidence that I told you that the authors didn't construct the algorithm with that in mind. It's a coincidence that this is SGD, like in the sense that the expected value of this is lambda times WT. The aim of having those dual variables there was not to approximate lambda times WT, in which case alpha IIT would be a very bad approximation of WT. I could just use WT directly myself, in which case it would just be stochastic gradient descent. But the aim of the alpha IT there is not actually to use, the aim is not to use WT. It's to use you should think of these more as using the gradient information, a combined gradient information in an intelligent way. So that's the only intuition I can give you. It's like a post hoc thought. If I hadn't told you this, you would not have even thought that this is stochastic gradient descent. It's doing something. It has these dual coordinates, and it's like a dual coordinate ascent in some sense. And if you look at the original way the algorithm is described, it's completely different from these. It's just, this is not how the algorithm is written up in the original papers. This is just like I guess the authors tried to post hoc fit it into the framework of how to think about an SGD algorithm. And I understand your point that you think that this might be adding more variance, but maybe the way to think about this is really something like this. Alpha IT is not supposed to be an estimator of WT. That's not the point. It's supposed to be something else that when you add this, the variance of this term is not the sum of the variances of these two terms. So if you think that this term is estimating WT and this term has variance, That's not the idea. But that the variance of the sum of these two terms somehow cancels each other out, like in the sense that this has a decreasing effect on the variance of this, and the reason is really because of this, is that this thing can be written down as primal suboptimality plus dual suboptimality in some sense. And
delta fi and alpha are negatively correlated, so
yeah, exactly.
that's the variance, the covariance.
Yeah, exactly. Yeah. So it's not to look at that separately, and yeah, that's right. Sure. Yep.
So in the original stochastic gradient descent, they are actually minimizing the expectation over the way data are generated. So so how does the new algorithm actually prove the statistical convergence of the statistical risk?
Right. So this is a good question, which, come back round circle to the beginning of the lecture. I told you that the aim in machine learning is often to minimize the true risk, which is that guy up there, the second line, the expected value of some loss function, and that's the true risk. But what we are doing is minimizing some kind of an empirical risk, which has the regularizer. So Yu Xiang's question was, how does this do compared to actually minimizing the true risk? Like, what are the statistical properties of these algorithms? And I would say that that's pretty much an open question. For now, the only analyses of the statistical risk are actually of the SGD-like algorithms, and there is a proof by Botu and Busquet in 2008 that shows that one pass SGD, which is one pass through your data points of stochastic gradient descent, is actually kind of optimal for risk minimization. So there's an excellent paper that came out at the end of 2014. That was by I wrote a little blurb about it in the notes. It was by Agarwal and Leon Botu. And Agarwal and Botu just try to downplay the optimism of these methods a little bit. So it seems right now that we're very optimistic. We get the best of both worlds of gradient descent and stochastic gradient descent and things like that. Agarwal and Botu prove lower bounds, but instead of having lower bounds in the stochastic first order oracle model, they have lower bounds in what's called the incremental first order oracle model, where you give an index I and it returns to you the gradient at that index, and then you give a different index I, it turns to you a gradient at that index, under which all of these algorithms fall, which is evaluating the at a single I. And so they give lower bounds for that, and they find that a lot of these algorithms are very close to the lower bounds, but not exactly equal to the lower bounds. So the lower bounds might be loose, or the upper bounds might be loose. But they also run a comparison, a theoretical comparison of two things, which is how is this related to minimizing the true risk, and in which they say that, okay, look, we still don't know, we know how these things do for this empirical risk, exponentially fast and all that is good, but how does it do for true risk? Still kind of uncertain, and still seems like single pass SGD is near optimal for true risk. And the second thing that they show is that these methods are not always better than gradient descent. Okay, so they're not always better, and the reason is quite subtle. The reason is that gradient descent in some sense works on the full loss function. So it works on capital F of W, while these methods work on Fi of W. And when capital F of W has strong convexity, okay, that means, what I mean by that is the average of those functions is strongly convex, but those individual functions are not strongly convex, then capital F of W has a strong convexity constant that's much larger than lambda. Okay, the simplest example of that is least squares regression, where you're minimizing yi minus xi transpose w the whole squared plus lambda by 2 w squared. Okay, now each of the functions fi is just one of these. It is not strongly convex. It is just a single one of these guys. It's not strongly convex. But if I rewrite this as y minus x w the whole 2 norm squared, you'll remember that the strong convexity of this loss, this overall loss, depends on the rank of x. And when n is really large, when you have a lot of data points, x is full rank, and this is strongly convex. And this is strongly convex with a parameter which is the the minimum eigenvalue of X transpose X. So basically what I'm saying is that capital F of W has a strong convexity which is some lambda min of X transpose X plus this regularizer. But when I do these methods like SVRG or SDCA, I'm only working with the strong convexity of lambda. So the rates that you see for gradient descent where you have a condition number times log of 1 by epsilon, those use the condition number of the overall function capital F. And they use the Lipschitz constant and the strong convexity constant of the overall function capital F. And it turns out that the Lipschitz constant of the overall function can be smaller than the Lipschitz constant of the individual functions. And the strong convexity constant of the overall function can be larger than the strong convexity of the individual functions. So those two bounds that you're seeing there are not immediately comparable. Okay, because the strong convexity and the Lipschitz parameters for gradient descent are different than for this. This one uses the piecewise, it uses the strong convexity and the Lipschitzness of the piecewise parts, but gradient descent works on the whole function. So it's a very nice paper by Agarwal and Bhattu that not only prove lower bounds, but also talk about some cases in which gradient descent is optimal, and these methods don't show an improvement, but there are other cases in which these methods do better. And so it requires a little more subtle analysis. So definitely a lot of open questions left in this area, and like over probably the next couple of years, you'll see a lot of activity. And maybe the one takeaway message is if you end up in your practice ending up with problems like that, remember that brute force, gradient descent is not always the best option. I think Nicole had a good example where she was running logistic regression on that, and then I told her about the SAG algorithm, and it sped up her thing by 17 hours. So the computation took 17 hours less by using SAG as opposed to gradient descent for logistic regression on that function. So that was just an example from one of your TAs from last year. But this could really help you a lot if you're actually dealing with real data and minimizing something of that sort. You should consider using some of these algorithms. Okay, thank you.